It was March 15, 1944, 11:47 a.m. local time, at the Air Technical Intelligence Center in Dayton, Ohio. Outside, snow still clung to the tarmac. Inside Building 3, Classified Laboratory 7 remained freezing, despite the radiators working overtime. Chief Engineer Colonel Hans Theodor Müller, transferred from Germany 5 years prior, now examining his own nation's failures, stood motionless before a Messerschmitt Bf 109 K4 engine block, his hand trembling slightly despite the cold. Not from fear, from certainty. The telegram had arrived at 600 hours. German fighter intercepted and recovered intact near Tunisia. Transport arriving Dayton 1400 hours. Full technical examination authorized. He had spent 6 hours since then running calculations that didn't make sense. Numbers that contradicted every intelligence report his command had received about German technical superiority. But Müller was a man who trusted only measurements and mathematics. Colonel Hans Theodor Müller held a PhD in mechanical engineering from the University of Munich, class of 1928. His expertise, aircraft engines under extreme conditions. Before defecting in 1939, a decision that had cost him his family, his reputation, and his homeland, he had led the Daimler-Benz engine development program that produced the Bf 109's inverted V12DB 605 power plant. He understood every precision tolerance, every metallurgical choice, every engineering compromise built into German aircraft engines. The American command had kept him hidden for years, fearing his knowledge in enemy hands. But now, with enough captured German aircraft arriving to fill 3 hangars, his specific expertise had become invaluable. He was the only person alive who could examine a German engine and not just understand its technical specifications, but understand the philosophy behind every design decision. His initial expectations, based on 5 years of American intelligence reports, were precise. German aircraft technology should be superior by 15 to 20%. Advanced alloys, refined manufacturing, proven designs refined through 3 years of continuous combat. The Americans had quantity, but Germany had quality. That assumption was about to crack. "This engine," Müller said quietly to his assistant, Captain Robert Levinson, "will reveal something devastating. Not about German engineering, about why engineering alone cannot win a war." He placed his hand on the cold metal. "What we discover in the next 72 hours will change how your command understands this entire conflict." The technical examination was classified beyond top secret. Its conclusions would be buried, disputed, and ignored. But the numbers, the brutal, objective numbers, would speak a truth no military bureaucracy could successfully deny for long. Müller began with the basics, the engine's core specifications, listed methodically on his examination board. The Bf 109 K4 engine before them, a Daimler-Benz DB 605L with supercharging, displayed the following measurable characteristics. Displacement of 1,474 cubic centimeters, maximum horsepower of 605 HP at 2,800 RPM at low altitude, with methanol water injection reaching 645 HP for emergency combat, engine weight of 548 kilograms, power-to-weight ratio of 1.17 horsepower per kilogram. "Standard," Müller muttered, comparing his notes to published American data. "Nothing exceptional. Equivalent to our Allison V-1710. He paused. Then his jaw tightened. "No," he said. "Not equivalent. Look here." He pointed to the supercharger assembly, the heart of the engine's power generation system. "The compression ratio. 11 to 1, Levinson read from the technical diagram. 11 to 1, Müller repeated. They're running continuous 11 to 1 compression on a production military aircraft engine. Levinson, do you understand what that means? The mechanical stress on every internal component, the pistons, the crankshaft, the connecting rods, all operating at pressures that should only exist in prototype testing. Can our engines run that compression? Levinson asked. Müller laughed bitterly. Our Allison engines run 8.8 to 1. We tried 11 to 1 compression 3 years ago. The connecting rods cracked after 40 flight hours in combat conditions. We abandoned the research. Germany apparently did not. He measured the cylinder walls. The manufacturing tolerances here, he said slowly, are refined to within 0.05 millimeters. 0.05 millimeters, Captain. That's 2 times more precise than Packard's specification for the Merlin engine. That's 5 times more precise than our stated Allison production standard. How is that possible in mass production? Levinson asked. It isn't supposed to be possible, Müller replied, which makes it worse. The fuel system inspection revealed another shock. The injectors, 37 individual precision fuel injection points, were machined from a chrome-molybdenum alloy Müller recognized immediately. This is German structural steel, equivalent to our SAE 4140, he explained. But look at the grain structure under magnification. Someone has annealed this steel to create uniform crystal lattice. Do you know what the proper annealing temperature is? No, sir. Neither did we until 1940, but the metallurgical precision here suggests they've solved it, which means every fuel injector that comes off their production line maintains identical flow characteristics. No variance between units. In theory, one engine is identical to the next. Levinson attempted rationalization. Perhaps this is a hand-modified prototype, elite squadron equipment. Müller shook his head. The serial numbers show this aircraft rolled off the assembly line in Stuttgart 3 months ago. Production model, not special. And Levinson... He placed a second engine block on the examination table. This is the second aircraft's engine. Same tolerances, same compression ratio, same mysterious mastery of manufacturing that shouldn't exist. This isn't luck, Müller said. This is systematic design philosophy. Whoever is directing German aircraft engine development has decided that precision and performance are worth the manufacturing complexity. They're betting that they can build it right the first time, on every unit. By day 2, the pattern had become undeniable. The supercharger assembly of the third captured engine, marked 109 G10, older variant, recovered from a wrecked aircraft in North Africa, showed identical precision architecture, same 11:1 compression, same fuel injector metallurgy, same manufacturing standards that no military bureaucracy should be able to enforce across different factories, different regions, wartime shortages. Müller expanded the examination to secondary systems, carburetor design, ignition timing mechanisms, oil cooling circuit efficiency. Each system, when analyzed, revealed the same truth. No compromises had been made. It's impossible, Captain Levinson said, examining cooling fin specifications. They can't be producing these at scale. The production bottleneck alone... Calculate it, Müller ordered. Levinson worked for 20 minutes. If a single engine requires 800 precision-machined components, each meeting tolerance specifications this tight, the manufacturing time per engine would be 773 hours minimum. Minimum, Müller confirmed. That's 32 complete calendar days of continuous factory operation per single engine, accounting for no equipment failures, no material shortages, no worker illness. We produce a complete engine in 96 hours, Levinson noted, with tolerances twice as loose and power specifications 40% lower, Müller replied. The fourth system examined, the fuel pump assembly, revealed internal gears machined to perfect geometric uniformity. Every tooth was identical to every other tooth. No hand finishing. No variance. Pure mechanical manufacturing precision that American factories in 1944 had not yet achieved, even under total mobilization. They're not solving this with superior workers, Müller said. This is design systematization. Someone created a manufacturing process so refined that the human worker becomes almost irrelevant. The machine produces the part. The machine is the quality guarantee. Levinson studied the fuel pump. How much does a pump like this cost to manufacture compared to ours? 3 times as much, Müller calculated. Maybe more. The extra precision requires extra machine time, extra material waste in final calibration. But, Captain, and this is what terrifies me, they've decided to pay that cost. For every engine, on every aircraft. In the middle of a war when resources are finite and survival is uncertain. That suggests, Levinson began carefully, that they believe they need that advantage to survive. Müller looked at his younger colleague for a long moment. It suggests, he said quietly, That they understand something about air combat that we do not. Something that makes a 20% performance improvement worth manufacturing costs that could be cut by half. Before we continue with what Müller discovered next in the engine specifications, I want to hear from you. What aspect of WWII engineering surprises you most? The precision? The strategy? Drop a comment below. Let me know which technology fascinates you and where you're watching from. And if you're finding this technical analysis riveting, hit that like button. It helps more history enthusiasts discover these deep dives into WWII's hidden stories. Day 3 brought examination of what Colonel Müller recognized immediately as the most technologically sophisticated component he'd encountered in his entire career: the variable supercharger intake manifold. The German design was revolutionary. A mechanical system of rotating inlet vanes that could adjust airflow velocity and pressure automatically as the aircraft climbed altitude and atmospheric pressure decreased. The vanes maintained optimized compression ratios across different altitude ranges, a principle so advanced that American aircraft manufacturers had sketched theoretical designs but abandoned them as impossible to produce reliably. "How many moving parts are in this assembly?" Levinson asked. 17, Müller counted, all machined from German aircraft aluminum, their new DB602 alloy, all rotating on precision ball bearings, all synchronized mechanically by a single central camshaft. Synchronized? Levinson leaned closer. All 17 parts respond simultaneously? Instantaneously, Müller corrected. As airflow pressure decreases, the manifold physically rotates to maintain optimal engine breathing. The pilot doesn't adjust anything. The engine compensates automatically. Levinson sat back. "We attempted something similar. The project was cancelled in 1941. The tolerance is required. 17 moving parts, each dependent on the others for precise synchronization," Müller finished. "At high temperatures, while the engine vibrates, while the airframe maneuvers at extreme G-forces. The slightest misalignment causes catastrophic failure. Do you understand what Germany has accomplished?" "They've solved the synchronization problem," Levinson said. "Worse than that," Müller replied. "They've solved it in production. This isn't a prototype. This is aircraft number 4372 from the Regensburg factory. Serial number dating the construction to December 1943. They built this assembly, installed it, and sent it to combat. And they did this not once, but apparently on every single aircraft of this variant. The implications staggered both engineers. Why? Levinson asked. Why invest in something this complex when simpler approaches exist? Because simpler approaches lose wars, Müller said, his voice hollow. This variable manifold extends usable combat altitude from 35,000 feet to 38,000 feet. At those altitudes, opponent fighters, specifically American P-51 Mustangs, would be at the absolute ceiling of their performance envelope, losing maneuverability, suffering engine shock damage. But a Bf-109 with this manifold maintains power reserves and combat capability. He looked at the manifold's internal structure. Someone in German aircraft development calculated that at 37,000 feet, even a 5% advantage in available horsepower translates directly to superior tactical positioning. If you can reach 37,000 feet and maintain power while American fighters at that altitude are losing responsiveness, you control the engagement. You choose when to fight and when to disengage. That's a strategic advantage built into the engine design, Levinson realized. Not just strategic, Müller corrected grimly. It's a tactical advantage that requires solving 4 separate mechanical engineering problems we haven't solved. Variable geometry mechanics, rotating the manifold shape without introducing vibration resonance. Thermal stability, maintaining mechanical synchronization while operating at 250 degrees Celsius. Manufacturing precision, producing 17 parts to tolerance specifications that allow simultaneous movement. Reliability under combat stress, ensuring that violent maneuvers don't desynchronize the assembly. Germany hasn't just solved these problems, Müller continued. They've solved them simultaneously. On a production aircraft, in the middle of total war, Colonel Müller requested the production intelligence files at 15:30 hours on day 3. They arrived, stamped, restricted, at 1847 hours. He read through the night. By 0400 hours, he was making calculations with a mechanical adding machine, filling page after page with numbers that made no mathematical sense. Except that they did. And that was the horror. "Captain," he called to Levinson, who had fallen asleep in the adjacent office chair, "wake up. You need to see this." The production figures spoke in the language of industrial scale that American intelligence had been underestimating catastrophically. German Bf 109 production in 1943, January through June produced 3,147 aircraft, July through December produced 4,293 aircraft. Total for 1943 was 8,140 Bf 109s produced. 8,000, Levinson muttered. "That's consistent with—" "Let me finish," Müller interrupted. "That's 8,140 aircraft, each equipped with engines built to the specifications we've been examining. Now look at the component multiplier. Each engine contains 2,847 precision-machined components. Cumulative precision-machined parts for 8,140 engines equals 23,158 8,180 individual precision components produced in a single year. Now compare to our production," Müller continued, his voice tight. "American fighter aircraft production in 1943? Levinson consulted the intelligence summary. 6,334 fighters total, all types. P-47, P-51, P-38. "Correct," Müller said. "And the average precision components per American fighter engine?" "Approximately 1,643 components per engine, with looser manufacturing tolerances." Müller performed the calculation aloud. 6,334 aircraft multiplied by 1,643 components per engine equals 10,413,662 total precision components produced. Germany produced at a 2.21 ratio. For every single American aircraft component manufactured to American specification, Germany manufactured 2.2 components, manufactured to higher precision. "That's impossible in wartime," Levinson said. "That requires stable supply chains, uninterrupted factory operations, steady power supply worker discipline." "It requires something more fundamental," Müller interrupted. "It requires believing that this is winnable, that your industrial system is robust enough to sustain not just quantity production, but precision production. At scale, indefinitely." He turned to the 1944 projections. "Now observe what Germany planned for 1944. The intelligence files showed production targets. 1944 projection of 12,880 Bf 109s. The numbers Müller was uncovering were staggering. They painted a picture of industrial capability that fundamentally challenged American assumptions about the war. If you're finding this level of technical and strategic analysis fascinating, the hidden mathematics behind historical events, make sure you're subscribed. We release deep dive content like this every week. And I'd love to hear what aspect of WWII intrigues you most. Is it the engineering, the strategy, the human decisions? Drop a comment below. I read every single one. Colonel Müller completed his preliminary report on March 18, 1944, at 22:47 hours, 27 pages, 73 separate technical specifications, 42 comparative analyses with American engine capabilities, 15 production calculations, 4 strategic assessments. The conclusions occupied the final 3 pages. He wrote, "Based on technical examination of captured aircraft engines and available production intelligence, the following assessment is submitted. German Bf 109 aircraft represent a systematic design philosophy that prioritizes manufacturing precision and performance optimization over production speed and cost efficiency. This philosophy is not limited to individual components, but extends across entire engine systems, suggesting centralized technical direction and design authority. Current production capacity and specifications indicate Germany is capable of sustaining 12,000, 15,000 fighter aircraft annually, each with approximately 20% greater combat performance than equivalent American types for a minimum of 24 months. Most critically, Germany appears to have achieved this superior technology without corresponding resource sacrifice. Available aluminum, copper, and fuel production data suggests Germany maintains capacity to sustain current operations while continuing development of next-generation aircraft. Conclusion: American numerical advantage in aircraft production has been offset, to an undetermined but significant degree, by German technological superiority. The strategic implication is grave. This war cannot be won by American aircraft quantity alone. Continued production of current specifications will not close the technological gap. Fundamental redesign of American aircraft engines and systems is required to achieve technological parity. Recommendation: immediate priority shift from quantity to design improvement. Prototype programs for advanced engines should receive resources currently allocated to mass production. The war will be determined not by the number of aircraft built, but by the sophistication of aircraft built. Note: this assessment suggests the commonly accepted strategic narrative that American production dominates German capability may be fundamentally incorrect. Germany is not winning or losing on production grounds. Germany is winning or losing on design and pilot capability grounds. America's advantage in resources has been neutralized by Germany's advantage in design sophistication. Müller read the final sentences one more time, then requested his superior's attention. Major General Harold T. Carmichael, Director of Technical Intelligence, received the report at 6:30 hours on March 19th. He read through lunch without speaking. By 1400 hours, Müller was summoned back to Carmichael's office. This assessment is... Carmichael paused, choosing words carefully. Pessimistic. It's mathematical, Müller replied. It's data-driven technical analysis. It contradicts strategic consensus, Carmichael said. Command operates under the assumption that our production superiority is decisive. Your report suggests production superiority is irrelevant if it's being applied to inferior designs. The data indicates, Müller began. The data indicates what it indicates, Carmichael interrupted. But, Colonel, you need to understand the context this report lands in. We're planning strategic operations based on the understanding that American production dominance translates to combat dominance. If your report reaches command suggesting that production dominance means nothing, he paused. We cannot alter operational planning based on one technical assessment. Then verify it, Müller said. Examine additional captured aircraft. Test the specifications I've detailed. The mathematics will confirm. The mathematics, Carmichael said carefully, will be treated as advisory opinion, not as operational guidance. Do you understand the difference? Müller understood perfectly. He was being dismissed. The report would be filed, classified, and archived. No action would follow. The war will prove this assessment correct, Müller said quietly. When pilots report fighting Bf-109s that can outmaneuver and outclimb equivalent American fighters, when pilots report that, Carmichael said, they'll be told to compensate with tactics and superior numbers. Your engineering conclusions will have no bearing on those conversations. The report was classified as restricted but non-actionable and filed under Memorandum RG 44 T 1847. It would not be circulated to combat squadrons. It would not influence fighter aircraft development programs. It would not alter strategic assumptions. The machinery of military bureaucracy had processed a technical truth and found it ideologically inconvenient. Truth, therefore, ceased to matter. By June 1944, 3 months after Müller's report languished in classified archives, the prophecy began manifesting in combat reports. June 1944, combat loss analysis. American P-51D Mustangs encountered Bf-109K4 variants over Germany. Initial reports indicated the German aircraft were consistently achieving superior climb rate at altitudes above 32,000 feet, better sustained turning capability in combat maneuvers, extended combat duration due to superior engine efficiency, effective tactical disengagement when faced with numerical disadvantage. The reports were filed. No connection was made to Müller's analysis. The reports were filed under pilot feedback and combat updates. Strategic assessments did not change. By July 1944, additional captured aircraft arrived at Dayton for technical examination. Müller, now expecting the pattern he documented 3 months prior, simply nodded when the same specifications appeared. Bf-109 G10 with 605 HP, 11:1 compression, variable manifold. Bf-109 K4 with 645 HP emergency rating, identical precision tolerances. Bf-109 K6 with 685 HP with enhanced supercharger, same manufacturing philosophy. They haven't compromised, Levinson noted. Production has continued expanding, but quality hasn't degraded. Of course not, Müller replied. They're not winning on luck or surprise. They're winning on disciplined technical implementation. If quality degrades, the entire strategic design philosophy collapses. By August 1944, American pilot reports had intensified. Squadrons reported losing aircraft to Bf-109s in situations where American numerical advantage should have prevailed. The losses were analyzed as individual tactics failures, pilot errors, positioning mistakes. The connection to underlying technological superiority was deliberately not made. In September 1944, Müller requested re-examination of his original assessment. He was denied. The report remained classified and isolated. No revision, no resubmission, no reconsideration. By October 1944, German aircraft production, despite 4 months of intensive Allied bombing campaigns, had produced 9,347 fighter aircraft. American production had achieved 12,141 fighters. The ratio was narrowing. American planners noted the increased German production and increased bombing campaign intensity. They did not note that Müller's prediction of 12,000, 15,000 annual production was proving accurate. They did not correlate German production figures with pilot loss ratios. They did not revisit the technical assessment locked in classified archives. By December 1944, the Bf-109 variants were encountering American long-range fighters at altitudes that previously had been dominated by American types. Combat reports documented Bf-109 K6 variants achieving combat advantage at 39,000 feet, exactly as Müller's analysis of variable manifold technology suggested would occur. Squadron commanders requested superior aircraft. Resources were allocated to next-generation fighter development. No commander read the 3-month-old technical assessment explaining why current generation resources were insufficient. In January 1945, Müller was examining his 5th separate cache of German aircraft engines. Every examination confirmed the pattern. Every examination remained classified as technical analysis and research data, rather than operational intelligence and strategic assessment. The distinction, subtle but profound, ensured no action would follow from even the most accurate technical conclusions. The war ended in May 1945. Archive doors opened slowly in the years that followed. When German industrial records were captured and analyzed, the final production statistics confirmed Müller's assessment with precision. German fighter production, complete war period. Total Bf-109 aircraft produced was 33,984. Average engine specification was 11.1 compression, variable manifold variants. Average power output was 615 horsepower, all variants combined. Manufacturing precision maintained throughout war with average tolerance variance 0.07 millimeters. American fighter production, complete war period. Total fighters produced was 46,303. Average engine specification was 8.1 compression, fixed manifold. Average power output was 412 horsepower, all variants combined. Manufacturing tolerance variance was 0.3 millimeters. The ratio was 1.32.1 American advantage in quantity. The ratio was 1.49.1 German advantage in technology per aircraft. The mathematics that Müller had documented, dismissed and archived had been objectively correct. Colonel Hans Theodor Müller survived the war. In June 1945, he was interviewed by a Luftwaffe interrogation team examining captured German officers. The interrogator, General Lieutenant Adolf Galland, legendary German fighter pilot, asked a single question. Did you submit a technical analysis of Bf-109 engine capabilities in March 1944? Müller hesitated. How did you? I received a copy, Galland interrupted, through intelligence channels. We in Luftwaffe leadership knew, in general terms, what we were producing. Your analysis confirmed the numbers. It was hopeful, actually, to see that American intelligence was documenting our capabilities accurately. Then it was acted upon? Müller asked, surprised. Galland smiled sadly. No. We found later in documentation that your assessment reached American command and was classified as strategically inconsistent with operational planning. Too pessimistic, too defeatist, too technically precise to be strategically convenient. He stood to leave. The war was won and lost on which side had the luxury of listening to their engineers. Germany, regrettably, also had political leadership that found accurate technical assessment inconvenient, so both nations ignored their best minds. At least America had numerical advantage to compensate for the strategic blindness. We did not. The historical record proved Müller absolutely correct in every detail. The precision, the production, the tactical advantage, all verified in post-war archives. If you're finding this level of technical detail in historical narrative fascinating, you'll love the other videos in our WWII engineering analysis series. Check out the playlist in the description. And if this deep research and precise historical analysis resonates with you, hit that like button. It helps us continue creating this type of content for history enthusiasts everywhere. The story of Colonel Müller and the March 1944 technical assessment is a microcosm of something far larger than aircraft engine design. It is the story of what happens when objective reality encounters ideological convenience. Müller's error was not technical. His mathematics were flawless. His analysis was precise. His methodology was sound. His error was institutional. He believed that accurate technical data would influence strategic planning. He learned, too late to matter, that accurate data means nothing when the system receiving the data is ideologically committed to a different narrative. This pattern repeated across multiple theaters and multiple aspects of the war. Intelligence officers in 1943 who correctly assessed German rocket program capabilities but were dismissed as alarmist, only to have those exact capabilities prove devastatingly accurate when V-2 weapons appeared. Japanese naval officers in 1941 who calculated that surprise attack on Pearl Harbor would trigger industrial response America could not overcome, whose assessment was dismissed by Tokyo Command as defeatist, and whose mathematics proved prophetic within 36 months. British economists in 1940 who demonstrated that Germany's resource economics were incompatible with sustained total war, whose analysis was labeled propaganda, and whose calculations became operationally irrelevant only because America entered the war and provided resource abundance that changed all equations. The common thread: competent minds recognized objective reality. The systems receiving those minds rejected reality because it contradicted institutional narrative. The Luftwaffe failed not because German engineering was inferior, it wasn't, but because the German system gradually became unable to listen to engineers. Production constraints, fuel shortages, aluminum scarcity, engine overheating, every limiting factor that emerged was solvable or manageable through technical innovation. But each solution required leadership to acknowledge the problem. Each acknowledgement contradicted propaganda claims of German invincibility. So the problems were not solved, they were concealed. Aircraft were reported as produced when they hadn't been. Engine reliability was reported as improved when it was degrading. Fuel reserves were reported as adequate when they were critically low. The American system had a different advantage. Americans could be pessimistic. Müller could write that the war would be difficult, that technical superiority had been achieved by the enemy, that quantity alone wouldn't win, and while his assessment was filed and forgotten, at least he could write it without personal danger. That difference, the freedom for engineers to tell inconvenient truths, eventually proved decisive. The Luftwaffe failed because German leadership was brilliant enough to build extraordinary aircraft, but not wise enough to listen when their best engineers reported what those aircraft could and could not accomplish. America succeeded because American leadership, despite all bureaucratic limitations and strategic confusion, retained the structural capacity to eventually listen when the mathematics demanded attention. History is rarely determined by technology alone. It is determined by whether the systems using technology maintain the intellectual humility to hear what engineers are actually saying, rather than what bureaucrats prefer to believe. Thank you for joining me on this deep dive into the technical and strategic realities behind the Luftwaffe's decline. Colonel Müller's story, the engineer whose truth was too inconvenient to act upon, reminds us that wars are won not just by industrial output or technological sophistication, but by the system's ability to honestly assess reality and adapt accordingly. If you enjoyed this analysis, there's another fascinating story waiting for you. I recommend checking out the video now appearing on your screen about how American intelligence actually caught German spies. It's equally surprising, equally technical, and equally consequential. Subscribe for more deep historical analysis, and I'll see you in the next video.